Today we are going to discuss another problem on root locus. So the question is, sketch the root locus of the system having open loop transfer function g of s into h of s that is equal to k divided by s into s plus 2 into s square plus 2s plus 2. Sketch the root locus of the system having open loop transfer function as follows. So we know the first step is to identify the location of poles and open loop poles and zeros. So here the location of poles are at s is equal to 0, minus 2, and the other poles are at minus 1 plus or minus j1. You can see that since there is only gain k in the numerator, there will not be any open loop zeros, only open loop poles are present, and the number of open loop poles n is equal to 4. Here number of open loop zeros m is equal to 0. So how many root locus branches will be there? Since there are 4 open loop poles, the number of root locus branches will be equal to 4, and we can say that all 4 root locus branches that are starting from 4 poles will end at or terminate at 0, that is at infinity. So now the next step is to find the centroid. So we know the equation of centroid is sum of poles minus sum of zeros divided by n minus m. So the sum of poles are minus 2 plus or minus j1, that will be 0, and minus sum of zeros by 4. So that is equal to, centroid is equal to, we will get centroid equal to minus 1, because minus 2 there is one pole, 0 there is another pole, then another 2 poles are complex conjugate pairs at minus 1 plus or minus j1. So when you find the sum of all these, we will get minus 4, and there are no open loop zeros, hence this term is 0, divided by n minus m, that is equal to 4. Now the next step is to find the angle of asymptotes. So the equation for angle of asymptotes is plus or minus 180 degree into 2q plus 1 divided by n minus m. What is the value of q? You have to take the value of q as 0, 1, 2, etc. up to n minus m minus 1. So we have to take the value of q up to from 0, 1, 2 and 3. n minus m 1 minus 1 is 3. So when the value of q is equal to 0, we will get the angle of asymptote is plus or minus 180 divided by 4, that is equal to plus or minus 45 degree. And the value of q is equal to 1, we will get plus or minus 180 into 3 by 4, that is equal to plus or minus 135 degree. And the value of q is equal to 2, it will be plus or minus 180 into 5 by 4, so it is actually equal to plus or minus 225 degree. Actually what is plus or minus 225 degree? It is minus plus 45 degree. Now if you write the equation for q is equal to 3, so what is q is equal to 3? Q is equal to 3 is plus or minus 180 into 6 plus 1, that is 7 by 4, that is sorry, the plus or minus 225 is actually equal to minus plus 135 degree, and when q is equal to 3, we will get the value as plus or minus 315, which is again is equal to plus or minus 45 degree. Now we have to draw the asymptotes with respect to what? With respect to the centroid. So from this point minus 1, we have to take plus 45 degree and minus 45 degree, and again from the centroid we have to take plus 135 degree and minus 135 degree. So when we draw the asymptotes, we can see that the asymptotes are like this. So these are the asymptotes, the lines that shows in this violet color are our asymptotes. So we can see the asymptotes that is in the figure as plus 45 degree and minus 45 degree, again plus 135 degree and minus 135 degree. Now what is the next step? The next step is we have to find whether there is any breakaway point for the given problem, whether there is any breakaway point. So for that we have to write the characteristic equation of the system, and if we write the characteristic equation of the given system, we can write the characteristic equation of the system as s raised to 4 plus 4s cube plus 6s square plus 4s plus k equal to 0. From where did we get this characteristic equation? We already have g of s h of s, okay, that is given in the question. G of s h of s is given in the question, and we know for the closed loop system the equation of transfer function is g of s divided by 1 plus g of s into h of s. This is the transfer function equation of closed loop system. So when we know g of s h of s, by taking the equation 1 plus g of s h of s equal to 0, we will get the characteristic equation of the given system. So this is the characteristic equation. Now we have to write an expression for k from that. So k will be equal to minus of s raised to 4 plus 4s cube plus 6s square plus 4s. Then in order to find whether there is any breakaway point or break-in point, first we have to find the first derivative of this k with respect to s, that is dk by ds, that is equal to 0. This dk by ds will be 3s cube plus 4s cube plus 12s square plus 12s plus 4 equal to 0. Now we can rewrite this equation as the equation for dk by ds as, when you take 4 common in the given equation, we can write the equation as s cube plus 3s square plus 3s plus 1 equal to 0. By solving this equation, we will get s plus 1 whole cube equal to 0, or the value of s is equal to, the roots of this equation is minus 1 and minus 1. Now what is the next step? We have to find whether this minus 1 is an actual breakaway point or not. So we can easily understand from this graph that we already have this minus 2 and 0. There are two poles at s is equal to 0 and minus 2. So there should be two root locus branches that starting from this. So before that, going to further, we have to find out whether any root locus segment that is in the real axis. What we do for that? For that, we have to take any arbitrary point. Let me take minus 0.5 as an arbitrary point. Check the right hand side of that point and count the number of real poles and zeros to the right hand side of the point minus 0.5. So here there is only one pole, and which is an odd number to the right hand side of the point minus 0.5. Hence we can conclude that the point minus 0.5 is included in the root locus. Also, when you take any point in between this 0 and minus 2, the number of open loop poles and zeros in the real axis to the right side of that point is only 1, and that is an odd number. Hence we can say that this line segment, that is the line segment that is starting from 0 to minus 2, that will be included in the root locus. So I am marking the root locus as a red line. And when you take another point, that is, we can take another point as minus 3, another arbitrary point minus 3. So when you take another arbitrary point minus 3, please check the right hand side of this minus 3 and count the number of open loop poles and zeros in the real axis. So to the right side of this minus 3, the total number of open loop poles and zeros in the real axis is 2. That is an even number. Hence we can conclude that this minus 3 is not included in the root locus. The point minus 3 is not included in the root locus. So if you take any point from here, that is minus 4, minus 5, etc., it will not be included in the root locus. So the only part that is included in the root locus in the real axis is the line segment that is starting from 0 to minus 2. So we already know this 0 to minus 2 is included in the root locus, and we got the breakaway point as minus 1. That means the two root locus branches that starting from this minus 2 and 0 will meet here at minus 1. Okay, so that we know. The two root locus branches that start from this minus 2 starts from this minus 2 and 0, that will meet here at the breakaway point minus 1, and it will go asymptotically to infinity through any of these asymptotes, because we already have the centroid that is at again minus 1. So the asymptotic point or the root locus, path of the root locus will be through the asymptotes only. It will not cross the asymptote, it will be through the asymptotes only, since the centroid and breakaway point is same. The root locus branches that will starts from 0 and starts from minus 2 will meet at the breakaway point that is at minus 1, that we already got. S is equal to minus 1 is our breakaway point. So that will meet at this breakaway point, and from this it will go to infinity through any of these asymptotes. So the path will be through the asymptotes only. Okay, now there are another two poles, that is complex conjugate pair of poles are there. So we have to find out the angle of departure, since there is open loop complex conjugate pair of poles are there. We have to find out the angle of departure. So let this pole is be A, let this pole is A, and we can write this is A and the pole that is below is A complement. Now we have to draw or mark straight lines from all the poles and zeros to the complex pole A. Now mark the angles as theta 1, theta 2 and theta 3. So we can see that here there are no open loop poles, there is only, here there are no open loop zeros, only open loop poles are present. So in order to find the angle of departure, what is the equation for angle of departure? The equation for angle of departure is 180 minus of sum of angles of poles. 180 minus sum of angles of poles. So what are the sum of angles of poles? Here we have theta 1 plus theta 2 plus theta 3 as sum of angles of poles, plus sum of angles of zeros. Here we do not have any open loop zero, so this term will be 0. So when you solve this equation, we will get the value as the angle of departure corresponding to the pole, complex pole A is minus 90 degree. Because theta 1 is, what is theta 1? You will get theta 1 as 45 degree, theta 2 that will be equal to 135 degree and theta 3 equal to 90 degree. You will get the values like this. Theta 1 is 45, theta 2 is 135 degree and theta 3 is 90 degree. So by substituting the values of theta 1, theta 2 and theta 3 in the equation, we will get the complex pole A equal to minus 90 degree. So corresponding, when complex pole A is minus 90 degree, what is corresponding to A complement, the other pole? The angle of departure of other pole is minus of minus 90 degree, that is plus 90 degree. So we got the angle of departure corresponding to the two poles. Corresponding to this pole A, the angle of departure that we can draw as plus 90 degree, minus 90 degree, and corresponding to this pole, that is complex pole A complement, we have the angle of departure is equal to plus 90 degree. Okay, so the complex pole A, the root locus branch that starts from complex pole A, it starts from this complex pole A, the root locus branch that starts from this complex pole A through the angle of departure plus 90 degree. Okay, it starts from this complex pole A through the angle of departure plus 90 degree. Okay. Again there is another complex pole A that coming to through the angle of departure minus 90 degree. Now in this problem, since the two complex poles are, the real values of two complex poles are minus 1, or it is actually in a straight line from the breakaway point. We already have the minus 1 as breakaway point, and you can see that these complex poles are at straight lines to the breakaway point, and the angle of departure of these two complex poles are plus 90 and minus 90. Hence, this is starting from the root locus branch that starts from here, that is coming to plus 90 degree, and here it is coming to minus 90 degree, and here it is coming to plus 90 degree. So in these type of problems, if it is in a straight line, okay, if the complex poles are in a straight line to the breakaway point and the angle of departure is plus 90 and minus 90, in these type of problems, these root locus branches will meet at the breakaway point, that is at minus 1. In these type of problems, these root locus branches that will meet at minus 1. So the two root locus branches that starts from the complex pole A will come to minus 1 through the angle of departure minus 90 degree, and complex pole A complement will again comes to minus 1 through the angle of departure plus 90 degree. So in these type of problems, this will meet at minus 1, and from here we already have 4 asymptotes. It will go to infinity asymptotically to these asymptotes. So here you can see that the breakaway point and centroid is same. That means the path of the root locus will be through the asymptotes. Since the centroid and breakaway points are same, the path of the root locus will be through the asymptotes. Now here we already have 2 root locus branches, because when it passes through the asymptotes, it will meet the j omega axis, right? So we have to find the angle of intersection of asymptotes with the j omega axis. Since I have already told you the path will be through the asymptotes, the meeting point will be this one for sure, but we can also calculate the intersection of j omega axis, that is by taking the characteristic equation of the system, that is s raised to s raised to 4 plus 4s cube plus 6s square plus 4s plus k equal to 0. Now substitute s is equal to j omega. When you substitute s is equal to j omega, you will get omega raised to 4 minus 4 j omega cube minus 6 omega square plus 4 j omega plus k equal to 0. Now take the imaginary parts separate. That means minus j 4 omega cube plus j 4 omega equal to 0, and that indicates omega square equal to 1 and omega equal to plus or minus 1. So what is the meeting point with respect to j omega axis? The meeting point with respect to j omega axis is plus or minus j1. That we already got here, okay, because the asymptotes are passing through plus or minus j1, and I have already told you the root locus, since the centroid and breakaway point are the same, the root locus branch will pass us through the asymptotes only. So we got the meeting point of asymptotes as plus or minus j omega 1, plus or minus j1. Now we have to find the value of k at the meeting point of the root locus with the j omega axis. What is the value of k? The value of k at the intersection of root locus with imaginary axis or j omega axis. So what we have to do for that, we have to separate the real part from the equation. So that will be omega raised to 4 minus 6 omega square plus k equal to 0. By substituting omega square equal to 1, we will get k is equal to 5. This is the value of k at the imaginary axis, or at this point of intersection here. Here the value of k is equal to 5. That means the system will be stable when the value of k is less than 5, and at k is equal to 5 the system will be marginally stable. Above k greater than 5 the system will be unstable. So we can draw the root locus branches now itself. That is, there will be 4 root locus branches, one starting from 0, other from minus 2, will meet at minus 1, another from the pole a, that is minus 1 plus j1, and another from the pole a complement, that is minus 1 minus j1. From these two poles the root locus branch starting through the angle of departure, and since these are in straight lines, it will meet here. Okay, it will meet here and break away from here. So we can draw the root locus branches. The 4 root locus branches will meet here, and it will go to infinity through the asymptotes. So this will be the direction of root locus. Okay, since these complex conjugate pair of poles are in straight line with this, then only this will happen. Okay, since these a and a complement are in straight line with the breakaway point, and the angle of departure of these two poles are minus 90 and plus 90. So because of that, this will meet here at this point. Thank you. Suppose I am just explaining one problem. Suppose there is a problem. Okay, suppose there is a problem which have 4 open loop poles, and this is not related to this problem. The problem with the open loop transfer function k divided by s into s plus 2 into s square plus 2s plus 2, that is over. So I am giving you another example. Suppose there is another problem with 2 open loop poles are in the real axis, and there is one complex conjugate pair of poles. Then in that type of problems, suppose the breakaway point is somewhere near. Okay, so one root locus branch that starts from here will meet here. Okay, so suppose you have the asymptotes like this. So the one root locus branch will go to these asymptotes, another will go through these asymptotes asymptotically. Okay, that is coming here, that will go through these asymptotes, and there are another complex 2 complex poles, that is at a and a complement. So this will move through their angle of departure, and it move asymptotically to these asymptotes to infinity. Here also Here also this will move to asymptotically to infinity like this. If the complex conjugate pair of poles are not in a straight line with breakaway point, the root locus will be like this. Approximately the root locus will be like this. So you can see the problems like this that are also available. Thank you.